All right, so I've already typed up these definitions, so I'm not going to handwrite them, but we are going to talk through them. So composition of linear transformations in terms of matrices. If we've got two transformation functions, T of A goes from Rn to Rk, and T of B goes from Rk to Rm. Well, we can compose these by putting together composing TB with TA. So we've got T sub B of T of A. So notice I'm going to put in T of A into my transformation. It works just like any linear composition. So I put in T sub A. Putting in T sub A means I go from Rn and I get out an Rk. I can put an Rk into TB, which is what we do. So we've got our two matrices, A and B. So our composition ends up being the matrix product of B and A. So as long as our orders match, then we can compose the transformations. But because the orders need to match, generally matrix composition is not commutative. So in this case, we couldn't compose T of A with T of B because T of B would output matrix M, but we need an N to put in. So our resulting transformation here is going to go from Rn, because that's what we put in first, and Rm is what we get out. All right, so we have identity as well. An identity transformation is just going to give us back our matrix X. And we need the identity operator because that allows us to get an inverse. So if we have an inverse, then T sub A composed with its inverse is going to give us the identity. And by using this idea, we can solve for our inverse. The geometric implication of this is that we've got our point W, which is an image of X under our transformation, and then the inverse would map W back to X. To find an inverse, we have to have a one-to-one transformation. We know that it's one-to-one if our matrix A is invertible.